Alright guys, so we have placed our entire problem in a mathematical framework. The problem of trying to strengthen our bike, which essentially happens when carbon diffuses from the surrounding into my rim, and that particular behavior is rather expressed by these couple of expressions here. Now we intend to solve this expression here, as it will give us a relation to understand or to determine how my concentration is going to change with respect to my position and time. Now in order to solve this, we will consider a system that is simpler, meaning a system that is one-dimensional. So if I consider a one-dimensional system and the diffusion of carbon in that one-dimensional system, like the line that we considered in our in the original container, the change in concentration across that line with respect to time can be expressed in this way here. So I have my original law that describes how my carbon concentration is going to change with time. Now what essentially I'm doing is I'm considering just one line in my system, not my entire system. So if I consider how along that line my concentration is changing with respect to my position and time, I end up having, or I end up reducing this expression, this second law, into something like this. Now in order to solve this, of course, all these terms have specific units associated with them. When I consider a line, when I consider a different position, I have units associated with them. When I consider time, of course, there is some unit associated with it. And when I consider this constant here, the diffusivity, there is a specific unit associated with it. Now in order to solve this mathematically, we want to reduce or get rid of all these units. So we begin by non-dimensionalizing these different parameters or these different entities here. So we begin by non-dimensionalizing my position or the distance x. So in case of dimension or in one-dimensional system, my position can be rather described by my distance from the origin. So that is given by my x. So using my length L, I'm non-dimensionalizing it. So if I assume that this is the line that I'm considering, AB, and along this line I want to consider how my concentration is changing. Maybe it's originally like this, and with respect to time, how this is going to evolve is what I'm considering. If I assume that the entirety, in its entirety, the length of this line AB is L, so we call it as a characteristic length, then I can non-dimensionalize my individual units of length, that is x1, x2, these individual units of length that also describes my positions. The unit of length that I use to describe my position, I can non-dimensionalize it by the ratio of x and L. So x gives me my position, the length that gives me my position. I'm taking the ratio of x with respect to my characteristic length. So this is going to get non-dimensionalized. So this is the non-dimensional variable of my position. In the same way, I'm going to consider a characteristic time T0. Let's assume that this T0 is the time required for my concentration to become homogeneous across this line. So when I take the ratio of this T0 with respect to any given time T, I end up having a non-dimensionalized time variable. So I have a non-dimensionalized spatial variable. I also have a non-dimensionalized time variable. The non-dimensionalized spatial variable, I arrive at it by the ratio of x to that of L. L is the characteristic length. In this case of the time, I arrive at the non-dimensional time variable by taking the ratio of my time t to that of my time t0, which is the characteristic time here. Now, it is also possible for me to have originally the concentration described using a non-dimensional unit, meaning if I express my concentration in mole fraction, then innately it doesn't have any concentration. However, to ensure that my concentration assumes a range of values, that is something that I can easily handle, I manipulate my concentration by introducing a new variable. Even though it is possible in the first place for me to express my concentration in a dimensionless way, it is possible for me to express it in mole fraction so that it innately doesn't have any dimension. It is possible for me to even more simplify the expression of or the description of concentration by introducing or expressing my concentration using eta. So what eta essentially tells is that when I have a concentration profile something like this, where this concentration here is the concentration at infinity and this concentration here is the concentration at C0. When I express my concentration using eta at C0, what essentially happens is my eta naught, so my eta at C0, this position here, the initial position here, so this is my x is 0, I call this as C0. In this case, my x tends to infinity, so I call it as infinity. The concentration at my x0, so I call it as eta naught, will be equal to, according to this expression, will be C0 minus C infinity divided by C0 minus C infinity, so it is going to be 1. On the other hand, if I consider my eta infinity, that is the concentration at infinity, so the revised concentration, the concentration expressed as eta at infinity. So what it essentially means is then C infinity, according to this expression here, C infinity minus C infinity divided by C0 minus C infinity. So this is going to be 0. So when I consider the distribution of concentration from 0 to that of infinity, when I express it in terms of C0 and C infinity, it can be any value. It depends on the material that I am considering. But on the other hand, if I express it in terms of eta, it is going to change between 1 and 0. And for this simplicity alone, since this makes expressing my concentration in eta makes my entire problem rather straightforward, we are rewriting the concentration using eta. So ultimately, my eta is going to vary from 1 to 0. So we are trying to solve this guy here. The first assumption we made is one dimension. The second thing we did is we non-dimensionalized our variables. The third thing is we ensured that our concentration is not randomly changing, but it is changing, or the range of my concentration is between 0 and 1. Now, having done all this, let us try to rewrite using these new terms. Let us try to rewrite our original expression for the one dimension. Now we have these three new terms that replaces our spatial position, that replaces our time, that replaces our concentration. Using these three terms, let's now rewrite the Fick's second law in one dimension. If I do that, we end up having this expression here. So we have non-dimensional. This expression now has the terms, the parameters that are the variables that are non-dimensionalized, and the concentration that varies between, or that changes between 0 and 1. Now we have this term, a constant here, that is dt by L, and for the sake of simplicity, L square. For the sake of solving this expression, for the sake of simplicity, let us assume this is 1. So dt, this set of constants, we assume it to be equal to 1. Now one way of looking at this is using this expression. When I make this assumption to be equal to 1, using this expression, I will be able to tell when there is when my diffusivity of my system is fixed, when my diffusivity of the system or my material that I am considering is fixed, I will be able to say, under this assumption, I will be able to say how long will it take for me to cover the distance of L. When I consider a system and there is a specific diffusivity, or there is a specific diffusion happening in that system across one-dimensional length L, and this diffusion is governed by the diffusivity constant d, under this condition here, this expression here tells me how long will it take for me to cover the distance L. Now, when I consider, so when I want to have this expression or this time using this relation here, I will be able to tell how long, when I play around with this expression here, I will be able to say how long will it take for my system or my diffusion to complete the distance of L. On the other way around, it can also be reversed and said, this expression here can help me, let me know for a given time t how much my concentration has diffused. So both these can be understood using this expression. Under this condition, both these can be understood from this expression here. Now when I make that assumption, what I essentially end up having is, when I make this assumption here, so this is just we just digressed, but now getting back to track. When we make that assumption and substitute it here, what we essentially end up having when we this expression here, it simplifies to something like this. So we assume this term to be equal to 0, so this simplifies to this. Now in order to further solve it, we introduce something called as a dummy variable. Now we want to solve this PDE, and the way to solve this PDE, the simplified PDE, is to convert it into ODE. And in order to convert it into ODE, now we introduce a dummy variable that is expressed as this. Now this dummy variable includes the position term, the non-dimensionalized version of x, and the time term, the non-dimensional version of my time. So the dummy variable I'm introducing, again this is introduced to convert my PDE to ODE so that I can easily solve it, and the way I introduce, the way this dummy variable is equated to the existing terms are in this way. The reason this particular representation is given, why my y is rather dependent on square root of tau, and this I here is because in case of this expression we take twice the derivative with respect to my position but just once with respect to my time. We are taking double derivative with respect to my position and just once with respect to my time. So therefore this y being written in terms of square root of tau and psi here makes sense. Again, in order to solve this, in order to convert this to an ODE, we are introducing a dummy variable. This dummy variable is the ratio of this term that represents my x and this term that represents my y. We just saw the reason why we have to have this in square root, because we are considering just once with respect to time, the change with respect to time once, but with respect to position twice. And that's the reason this is in square root and this is not. So using this dummy variable, when I rewrite this expression or when I solve this term here, I can rewrite this term as something like this. So I introduce my dummy variable here and I consider the left hand side of my PDE that I would like to solve. So using this dummy variable, the left hand side of the PDE can be expanded like this. Using your chain rule, it can be expanded like this. My y is the dummy variable. Now since I know my y is expressed as this relation would help me solve for this term here. I can use this relation to solve for this term here, and correspondingly the left hand side of my PDE would end up looking something like this. So essentially I introduce my dummy variable, rewrite my left hand side of the PDE using chain rule in this form, and this term I solve it using the relation of my dummy variable, and I end up having the expression like this. So ultimately now I'm able to have an expression for the left hand side of my equation, and that is something like this. Now I will consider the right hand side of my expression and try to solve it using my dummy variable y. So the right hand side of my expression, the PDE that I would like to solve, the simplified PDE that I would like to solve, can be expressed like this. And using the chain rule, now I can write the change in respect to eta with respect to my spatial non-dimensionalized spatial variable using my y in this way. So this I can write it something like this. Now once I have a relation for this, meaning once I have a relation for this from my description of y, so I can solve this from the description of y. Even this I can write it as this, I can write it as change in with respect to y and y with respect to psi. So even this term I can expand it like this, and when I do that I end up with an expression like this. So basically I'm expanding the change with respect to this spatial variable twice, once within the bracket and another time I'm doing it for this. When I do it twice, when I use my chain rule and replace my psi with y, when I do that, then ultimately I end up having an expression like this for my right hand side of my PDE. So I have my PDE, I took the left hand side first, I used my dummy variable, expanded my left hand side using my dummy variable and solved for my dummy variable through this expression and arrived at a relation, and this is the relation that I have. To consider my right hand side, I expanded it like this, and twice I expanded my change with respect to my spatial position or the spatial variable, and I expanded it like this twice. So by doing so, I end up having an expression like this. So all I need to now do is, I have an expression for my LHS, I also have an expression for my RHS, and all I need to do is equate these two. I end up having a relation like this. So I started off with a PDE, now I end up having a relation with a dummy variable y and eta. Now in order to make things even more simpler, I replace dou eta by dou y with p. So when I rewrite my dou eta by dou y with as p, then what I ultimately end up having is, what I ultimately can do is, I can then rewrite this expression here as this. So introducing my dummy variable, I have translated this ODE into something like this. Now my relation, that is how my eta, the concentration, is going to change with respect to my dummy variable, I represent it as p, and when I use this p representation, then I'm able to express this as this. So ultimately what you observe here is no longer a PDE but an ODE which we could solve. And when you solve this, you will end up having an expression like this, wherein you are able to understand how my concentration is going to change with respect to my position and my time. So when I solve this and substitute all the terms, replace all the non-dimensional terms with the actual terms, then and all etas with c, then I will be able to have an expression like this, using which I'll be able to find how my concentration is going to change, or what my concentration is going to be with respect to time and with respect to a given position. And of course I also have to replace my y with respect to this and then change it back to the dimensional variables. Yeah, when I do all this, then I'll be able to say how my concentration is, what my concentration is going to be with respect to my position and with respect to my time. Now, a primary objective of this lecture is to show how it's not rather straightforward to solve a PDE like this. So that is rather the primary objective. When you compare this derivation to all the other derivations that we have done, all the other derivations did not require too many substitutions. But if you consider this derivation here, it's a rather a simplified format or simplified form of the Fick's second law. Even the simplified form of the Fick's second law required several changes, required several translation of the variables. This was where we started. So this is what we essentially wanted to solve. To solve this, we began by considering, or we began by non-dimensionalizing. And then we began by expressing concentration in a way that was approachable for us. And then we introduced a dummy variable. And after that, we also introduced another dummy variable. So we introduced twice the dummy variable. It's once, and we also introduced another dummy variable. So this was y and this was p. And after that, even doing all this did not solve our expression. All this essentially changed our PDE to ODE. After reaching ODE, this we have to solve by looking back at all the understanding we gained from all the other sessions, and only then we will be able to arrive at this expression here. And again, this expression still has the dummy variable, so we have to go back and substitute this here and substitute back all these here so that we are able to get our original or the desired relation. So this is how the analytical solution works. It involves several substitutions, several considerations, introductions of several dummy variables, and then changing them back to the live variables. So this is the analytical approach. And of course, this analytical approach gives us a solution using which I'm able to find my concentration. Now what we will in the subsequent lectures will try to do is, we will try to approach solving this PDE using the numerical technique, using a numerical framework, and see which one rather suits us, or which one appears at least to be a much approachable when compared to the other one. So now we have seen the analytical approach. In the subsequent lecture, what we will do is, we will try considering the numerical approach like we discussed before, and we will see which of these two appears to be more approachable. So having understood how the analytical treatment works, we will consider the numerical treatment in the subsequent lecture. Goodbye guys.